Hello everyone. This tutorial is about the simulation of diverging pipe heat exchanger in which cold and hot water mix. The hot water enters the diverging pipe with 360 Kelvin and 0.001 meter per second, whereas 6 adjacent inlets carry cold water with different velocity and temperature. The velocity in cold water inlets arranged in diverging directions are 0.002 meter per second, 0.003 meter per second, and 0.004 meter per second, whereas temperatures 300 Kelvin, 290 Kelvin, and 280 Kelvin respectively. The pressure is standard, that is 101,300 Pascal. The dimensions of geometry are shown on the screen. A sketch considering symmetry for diverging duct will be drawn and then revolve around its axis. Using plane view, circles are drawn and extruded across the symmetry. So open ANSYS Workbench program and select Fluent package from Analysis for fluid flow. However, separate components can also be selected from System list. Right mouse click on Geometry and select New Design Modular Geometry. So according to dimensions of the geometry, set unit to millimeter. Now select ZX plane and click Y axis. Navigate to Sketching toolbox and click Line to form the sketch. Click at the origin. Form a vertical line. Then click at that point. Form a horizontal line. And then click to form a line with some angle. And join the line keeping it horizontal. So we got the sketch for our divergent pipe, but we have to revolve it around the axis. First we will set the dimension by clicking general and then set the dimension. So here L1 is 10 millimeter, L2 is 5 millimeter, while L3 is 100 millimeter. Now select the sketch and click revolve tool. And select the axis to revolve. Set operation to add frozen and click generate to obtain the divergent pipe. So this will be the inlet and this is the outlet of the heat exchanger for hot fluid. Now we have to draw the tubes for cold fluid, and for that click YZ plane and add a new sketch. Then go to sketching toolbox and select circle. Look from x-axis and on the axis draw 3 circles. And now set the dimensions. Also go to constraint and select equal radius so that these circles have the same diameter. Set the dimension for diameter of any circle, and here set 5 millimeter diameter Distance of first circle 15, for second 45, for third 75 millimeters. Now select the sketch of three circles and click extrude and apply for the geometry. Set operation as add frozen and direction both symmetric. Set the depth to 15 millimeter and click generate. So here we have the tubes for cold water inlet. Now merge all the bodies into one, and for this go to Boolean, unite, and select the bodies and click generate. Now name the bodies and the faces of this geometry. First we will name the faces. This one is inlet for hot water. So right mouse click on the face and click name selection and set the name to hot fluid inlet. Click generate. Now at the back, select the face, right mouse click, name selected and name it as outlet. Now name this face as cold inlet, which is at position 2. Name this as cold inlet 4. This one cold inlet 6. Now this one cold inlet 1. Cold inlet 3. Cold inlet 5. So we have all the faces named. Now select the body selection tool and click the body and name it as fluid domain. Now close the design modeler and return to the workbench program. Here you see a green tick next to the geometry option within your project. Now double click meshing. So let's generate a quick mesh. Here click generate. And check the mesh. We usually check the skewness, which is alright. Let's see if we add method and set method definition to tetrahedrons with patch conforming and then select generate. So close the meshing and return to the workbench program. Right mouse click on mesh and click update. There should be a green tick. So with this tetrahedron method, on the sweep faces, hexa mesh is automatically generated. But to fit the mesh, there is some prism-like 3D structure called tetrahedron used to fit the mesh. Now double click setup, click double precision and click OK. So in general setup, retain default for all parameters. Now double click models and double click energy to set the energy equation since there is heat transfer occurring in the system. Now we know that the velocities are very low, so set the viscous model to laminar and retain all the values to default. Now click materials and double click fluid. Go to Fluent database and select water liquid. Click copy and then close and then change, then close so that we can use water for our domain. Now go to cell zone conditions and double click the fluid domain. Set the material name to water liquid. Click OK. So that's it for the cell zone conditions. And for the boundary condition, first double click hot fluid inlet. Set the type to velocity inlet. Here click drop down list and click new input parameter. Name the parameter as hot fluid in velocity. Set the value to 0.001. Click OK. So this will generate a parametric table. By doing this, we can perform parametric analysis. We can change the input values and get the output. Now click thermal and do the same. Click new input parameter and set the parameter name as hot fluid in temperature. Set the value to 360. Click OK. Similarly, set the boundary conditions for cold inlet. For inlet 1, click edit, make sure it is velocity inlet type and set the new input parameter. Name the parameter as cold in 1 velocity. Set the value to 0.002 and temperature cold in 1 temperature. Set the value to 300 Kelvin. Okay, okay. Here the velocity is the same as cold inlet 1 and also thermal condition is also the same. Here the velocity is 0.003 and temperature is 290 Kelvin. Cold inlet 4 boundary condition is the same as cold inlet 3, but still for the parametrics we have to put input parameter with different name. Now cold inlet 5 and cold inlet 6 have the boundary conditions as 0.004 meter per second and 280 Kelvin. For interior and outlet, retain default settings. Make sure the outlet is pressure outlet. Now click Methods, and for the pressure velocity coupling scheme, select Simplex. Set spatial discretization gradient as green Gauss cell based, and all the discretization scheme to second order. Now click Monitors and Residual. Set the residuals to 1 exponent minus 6 for all the equations. Click Initialization and select Hybrid Initialization. Then click Initialize and then proceed to run calculation. So set the value of number of iterations to 1000 and click Calculate. So I will stop my recording here and let the solution to run. After the completion of calculation, close Fluent program. So you will see the parameters set here for the parametric analysis. Now double click on results to open post CFD. In order to obtain contour plots, a sectioning plane must be created. So for that, click locations and click plane, insert the plane and set ZX plane as the slicing method since our geometry is on ZX plane. So apply. You will see the section plane here. Now click contour icon and insert contour. Click plane as the location. Click temperature as variable and set the number of contours to 100. Then click apply. Here you can see the temperature contour on the sectioning plane of this heat exchanger. If you hold control button and rotate the wheel, you can rotate the geometry. So here the inlet enters the hot water which mixes with the cold and the temperature is varied. If you want to modify the legends, double click legend view and click appearance, select the size, set precision to fixed and then click apply. So here we have fixed values instead of scientific. Now, to obtain the velocity field distribution, generate a new contour plot or still click that contour and select velocity as the variable. Then click apply. You will see the velocity distribution. Now, if we want to get the contour over the whole geometry, we can click location and set wall fluid to main. Here set temperature as our variable and number of contours 200. Then click apply. Here you can see the temperature distribution on the wall of the heat exchanger. We can also obtain streamline and velocity vector plots from the commonly used options. So click streamline and select start from. We can select inlets by holding control button and click on the individual, or from here. So select all the inlets, click OK, set the number of points 200 and set the variable as velocity. Click apply and here we will get the 3D streamline plot. We can also obtain a surface streamline, and here we know that our surface is plane 1. So if we apply, we can get the streamline on this horizontal sectioning plane. We can also generate a plane in vertical orientation. So for this, select YZ plane and click apply. And we can see the streamline on plane 2. So we can check how the streamline is different from plane 1. Now check the vector plot for the velocity as our variable. We can select both planes and click apply. So here we see the velocity vector field. We can observe how the fluid is flowing and which direction the velocity vector is. Now let's calculate the outlet values of temperature and velocity. For this, click expressions and right mouse click to add a new expression. For outlet velocity, right mouse click on the definition box and go to functions, CFD post and area average. Right mouse click again and select the variable, which is velocity, and then location, which is outlet. Now click apply to get the outlet velocity. Right mouse click on the outlet velocity and set it as workbench output parameter. Now do the same for outlet temperature. Here the variable is temperature and location outlet. So the outlet temperature is around 305 Kelvin. Set this one also as workbench output parameter. So now we can perform parametric analysis. Close the CFD post and return to Workbench program. Now double click parameters. Here you can see many input parameters and the two output parameters which we selected in CFD post. Here we can have the outlet velocity and outlet temperature from these input variables. If we change the value of any variable, any input parameter, for example, we increase the hot fluid temperature to 400, and let's see what happens to the outlet temperature and outlet velocity. Click retain and right mouse click update selected design points. So here we can see that the outlet temperature is increased, which is now 313.79 Kelvin. We can change the other input parameters as well and get the output parameters. So thank you for listening. In this tutorial, we get to know how to create the geometry in Design Modeler using extrude and revolve tools, generating the mesh with tetrahedron patch conforming method, and define the materials with cell zone conditions in ANSYS Fluent. Then we set up the simulation problem using energy equation and laminar viscous model. Also, we get to know about the CFD post processing in CFD post and also how to perform the parametric analysis.